Okay, let's start up. I think I want to start on about page. Wait, what was it? I'll just show you with the screen share really quick. About page 100. Oops. Okay, we did this one already. We talked about maybe you guys can work on those. All right. So let me make a quick comment about page 101. We're not going to do these right now. I expect you to do them at home. But to be clear, I want to emphasize how to approach this entire page. Notice what is underlined here. Do not worry about FBDs and force equations for these problems. The idea with this page is to give you rapid fire practice in determining which of these friction equations applies and what is the direction of friction. Also, if there's more than one, figure out the appropriate direction for all these cases. Also, I snuck in one or two questions in this page where the problems are deliberately vague, and the answers try to talk you through those vagaries and say, well, if he meant this, it would mean this. And so the idea here is literally to give you practice on thinking about which of these equations apply. So after today's class, if you work on these, I think it will be pretty good. And so all of these problems, it's not trying to solve them. It's just trying to think about them. And so don't spend all day on these. Think about what you guess, then read the solution and see what comments I made about the problem. Then go on to the next one and just try and get through all of those in 30 minutes or something, right? About a couple minutes per. And there's about 10 questions there, I think. Something like that. All right. So that said, I'm now going to start with the same problems that I did earlier. And so if you watched the live stream earlier, I'm going to do the exact same problems because they're good problems and they're here for a reason. So we're going to start with 6.14. All right. So you can kind of read about this. And all right. I'm going to get my board ready. Okay. Six point 14. There's a block up here. I suppose I better get out the old classic here. All right. So you've had a second to look at that. Here's an idea. Okay. Imagine the stapler is sitting on top of this book, and I'm going to rotate the book slowly. Whoops. And then at some point that happens. It slides off. So now, just before it slides off, I was about at this angle. It doesn't matter exactly. But the idea was I basically started here and I just slowly raised this thing until the calculator or whatever was sitting on there, until it's just about to slide off. So right about at this angle, it's on the verge of slipping. Okay. So I keep losing my calculators all day because they fall down and get buried under here. Hold on. There's that other one. All right. Found some calculators. All right. So let's take a look at this problem here. The idea again was I keep tilting the ramp until the block is on the verge of slipping. All right. Now, if the block is on the verge of slipping, that should tell us something. I'm going to write down some choices for you. There's 3 different choices here. A, B, and C. Which one of these choices is a valid equation to use? One of these is valid.
B.
B, on the verge of slipping, friction is as large as possible. Now, if you remember, this is the largest possible frictional coefficient for this situation. Or sorry, this would be something like 0.5, and the kinetic is usually a little bit smaller, say like 0.3. Obviously, the numbers vary. If you used rubber, they'd be close to 1 or something like that. But in any event, so we've got some, the idea is if you're, oh, well, all right, good job. You identified this is the correct equation that we might use here. If it's on the verge of slipping, that's what gives us this idea right here. All right, so now let's get rid of these numbers. We'll keep that equation and get rid of the ones that don't apply. All right, actually, let me just rewrite it. If that's true, friction is mu static times the normal force. Okay, now this is a force problem. We're talking about friction, which is a force. What do we do with every single force problem we've ever had?
Draw an FBD.
All right, you called it. So give me one force acting on it.
Gravity.
Which way?
Straight down.
Straight down. Somebody else, what's another force?
Normal force.
Which way does that point?
Perpendicular to the ramp. So up
like
and
this?
to the right.
Oh, good. Very good. I was just being a jerk there. Nice job. All right. Is that it?
There's friction also.
Yeah. Whoops, this is a little bit off here. It's hard to draw from the side. It's kind of right angle-ish. All right. What looks like a logical coordinate system to use? What would you use for this one? Standard or rotated?
Probably rotated.
Yeah, I would probably use rotated too, unless you have a special problem. Usually on inclines, we use rotated. You could call whatever direction you want positive. I'm just going to call down the ramp positive because it fits well. What's the acceleration in this case? Which way is it accelerating?
It's not accelerating. Yeah.
Exactly. I was trying to trick you. Can't fool you guys at all anymore. You're all grown up. Oh, my physics students better than me. All right, whatever. Let's split these up. So I'm going to split up this mg, right?
That last part is wrong.
That's so wrong, isn't it? Doesn't that make you feel vile? So you can't have a component be larger than this, so that's clearly wrong. It's got to be parallel right there. And maybe I'll draw that in blue just to keep the color code here. There we go. Now look at it. Is this angle bigger than or less than 45?
Less than.
So what about this angle? Bigger than or less than 45?
Bigger than?
This one? All right. It's not obvious then. Let's go ahead and do it. If this is theta, what's that angle with the black dot?
90 minus theta.
So what's this angle in here with 2 black dots?
Theta.
So I was trying to draw it less than 45, but maybe I screwed up because I can't see from this side of the board, okay? So maybe I could try and make it look a little bit better. Just draw it a little bit better. Some's just hard to see. Let's exaggerate it slightly. There. Now it looks less than 45, right? Hopefully. All right, so this was mg, this was n, this was the frictional force. We already said this is x, this is y. We said acceleration is 0. So let's write out the force equations. In the x direction, what do we get?
Negative.
Oh, yeah.
Go ahead.
No, go ahead, dude.
Okay. Well, it's just negative friction equals 0. It's not accelerating.
There's another force in the x.
Oh, gravity. That is plus mg sine theta.
Yeah, and then usually we get in the habit of saying like that. Usually we put the positive ones first. Now remember, this is opposite. That's why this is mg sine.
Would it be good practice to just write mg sine equals f?
You could also do that as well. Esteban's saying, can't I just say that? You could switch it that, or you could say it like this. Either one is good. Let's keep going. Let's do the y direction now. Kev, you want to try it out?
Yeah, sure. In the y direction, there would be a normal force, so it'll be n. And the other y would be negative mg cosine theta.
Looking good.
And
yep.
Oh.
And then here, do you agree they're both equal to 0 because a is 0? Is everybody cool with that?
Yes.
Yeah. All right. Nice job. So now here's the idea. You're going to see this a lot. Okay. These problems are not that tricky. It's it's 2 extra steps. The first thing we do in these types of problems is 1, figure out if one of these equations applies. 2, do the FBD and the force equations. 3, the third step would be, well, if I want to use this equation for friction, usually I take one of the FBD equations, solve it for n, shove it in there, and I've got a new result for friction. Now, before we do that, let's read and see what we're supposed to be doing, because I've forgotten already. A good time to read. Okay, so which case of friction? We discussed that already. We did that. Okay, so we're trying to solve for the appropriate coefficient of friction. So here's the deal. We're trying to get this coefficient. We're not trying to get F. We're trying to get the coefficient. So that means we need to get it involved. But let's look at the things we know. Let's list out our givens. In this problem, usually you know the mass, G, theta. And so in this case, what are the things we don't know? N and F, right? You don't usually walk around knowing how much a floor is pushing on you or how much it's got friction on you. So in this case, I don't know N and I don't know F. However, I could figure out N because this is going to relate to these. So maybe I'll do that really quick. Now that I know the normal force, I could plug that into here and get the coefficient of friction involved. I don't want friction. I want the coefficient of friction. So I need to get this thing involved. Well, I could plug this into here, then plug that into there. Done. Let's do it. I'll race you to it. So take this, shove it into here, take that and shove it into there, then solve for mu. I'll meet you at the end. Okay? Race me. every term. I could divide every term by the same number. I could divide everything by 7. I could divide everything by 16, or I could divide everything by mg. It's just a number. As long as I do it to every term in the equation, well, the mg drops out. I don't even need mg. From there, we see which and all along I should have been, the angle in the picture was not theta, it was theta critical. So everywhere there's a theta, there should be a theta subscript c. Sorry, I forgot that earlier. Let's pause on that glare. What do you think? Is everybody cool with that?
Yeah,
Yep.
looks fine.
All right. And so here's the thing. We could do a quick calculation. Now I got to show you this one that's been pretty well. Okay, we'll do it with the stapler first. So, okay, we're just going to eyeball it there. What's that angle look like to you? Just kind of eyeball it there.
Like 45-ish, maybe 30.
It's probably less than 45. If I could somehow, because 45 would be like that, right?
Yeah.
So maybe it's half of that. So let's say maybe like 22, 23. Let's punch in the numbers and see what we get. So tangent, I'm just going to say 23 degrees. What the heck? So I get a coefficient of about 0.42, somewhere in that 0.4 range. All right. And so now check this one out. This one's been fun all day. I've got this calculator. It's like superhuman. No, so by the way, normally most objects, when you do this, the typical coefficients of friction, the largest we expect is the number 1. So if you're curious, think about this. Maybe this makes sense if I talk about it like this. Look, if this number is 1, what angle do you get? Well, at what angle does sine theta equal cosine theta?
45.
45. So usually things are going to slip at 45 degrees or less. Typically, these mu statics are less than 1. Now, here's the thing. This approximation that we're using is pretty, it's an estimate. It gets you in the right ballpark. But now watch this. I've got a calculator here. This thing has been doing some crazy stuff all day. Let's see if it holds up. See that calculator on there? Do you agree that angle is well over 45 degrees?
Yeah.
This calculator is like the mystical. Look at that. It's almost straight up and down. Oh my gosh. That is crazy. I have no idea what's up with this calculator, but it turns out to be a particularly bad choice for teaching students about this because it does not obey what we expect. It's well beyond. Like that thing was at 80 degrees almost, right? And so what happens here is in practice, there are other factors at work. In this calculator, this particular calculator, it's got these little rubber feet. And so for some reason, these rubber feet seem to be able to form a weak chemical bond with the textbook's cover or something. I don't know what it's almost like magic, because I've never, there are actually little blocks you could do, swage blocks in machining, where you could actually take them and push them together and twist them, and you actually form a weak chemical bond, and you can get a 90-degree angle. And literally, so there's some, I'll let you look that up later, or maybe I'll try and find the link about these blocks. But literally, you use them, and the surfaces are so perfect that you can get this weak bond just by putting them together. And it's great for machining, because then you could know these things are designed to know exactly, they're machined to extremely high tolerances, so you know how much space they take up. So you could use them to calibrate other spacings in your measurements and things like this. And so you could use these to calibrate your tools or a jig or something you're building. Anyways, there's reasons for these weird blocks, and I always forget, but it's just a very cool, obviously you have to take very good care of them so the surfaces remain like that, but you can literally stack and make whatever precise size you need. Very cool stuff. If you take a machine shop here at Hancock, John Garrity is a phenomenal instructor. So he knows a lot of interesting stuff. You can learn that from him in that class. So yeah, it's pretty wild. That is not a common response. Now, I've done this with hockey pucks, and routinely the angle is less than 45, but on rare occasions you'll get it up to like 60 degrees. So one of the things that I've also found with these things is, on average, this predicted value is pretty good. So let's say you get a coefficient of friction from a table in a book. That value is going to give you the average result if you did an experiment 100 or 1,000 times. Now, if you only do an experiment once, you could get a weird phenomenon like I just showed you, where we get this crazy angle close to 90. So there's weird situations, but on average, this model is decent, especially if you're using it for things like cardboard boxes on ramps and things like that, or ice cubes on concrete and things like that. So, all right. It's not a perfect model. On average, it gets pretty good results. All right. Let's go back to here and see what I want to say next. All right. So let's go to this one. Let's say we use twice the mass. How does the critical angle change? So if I used a block that weighs twice as much, what do you think would happen?
Well, you have a bigger normal force, right? More mg means more normal force.
But that wouldn't affect the critical angle. Isn't that just part of, like, it's constant part of the ramp?
Mass drops out, doesn't it?
Yeah.
You're right that you get more normal force, but don't you also get more frictional force in the same proportion? And that's what's cool about, and so we see that's the mass drops out. It doesn't matter. And this is approximately true too. You could do this with an experiment. Now, obviously, we're talking about the statistical average here. So if you do this a dozen times with one mass and a dozen times with the other mass, on average, they're going to end up being basically the same. So there's exceptions to that, and let's not go into them right now. So this is only an approximate model. It just gets the job done and gets us. If you're building something, right, and you look up these numbers in a table, I guess what I'm saying is don't believe them blindly. You could use these numbers to get a rough idea of something that might work, but then you would build a prototype and test it. So this physics knowledge is excellent for kind of ruling out things that have no chance of working. But just because it works on paper doesn't mean things will work out in the real world. So keep in mind there are limitations to the quality of this particular model of friction. All right. That said, let's go back there. Or was there a question? Well, I tell you what, let's finish these two out first. Let's say you use an angle above the critical angle. Does friction equal mu n? And if so, would we use mu static or mu kinetic? What do you think?
If it's above the angle, wouldn't we not use the U static, and instead of that we've been using U kinetic?
Correct. But this equation would still work as long as we just change the coefficient.
Mm-hmm.
Nice. What if we were below the critical angle?
Then friction is less than mu static.
Exactly. So this doesn't apply anymore, and friction is less than mu static times the normal force. However, if you're below the critical angle, we know something else. What do you know about the acceleration? If you're below the critical angle for this problem,
It's 0.
yeah, because it's not going to move. And so we know one less equation, but we also know A is equal to 0. So just to point this out, if it's just about to slide, we'd use friction equals mu static times the normal force. If it's above the critical angle, we'd use mu kinetic times the normal force as friction. And if it's less than the critical angle, this would not work. This would not work, but wouldn't that still work? And if so, friction is just this number, which is kind of going back to, I think, what Esteban was saying at the very beginning. He said, can I just say friction equals this? Yes, as long as it's at rest, or excuse me, as long as it's not accelerating, right? So there we go. All right, other questions?
So just to be clear, part D was, it doesn't really change the critical angle, right?
What
Or
was
does it?
part D? I forgot. Let me take a look. Hold on. Oh, part D is it doesn't do shit.
Okay, yeah.
Yeah. All right. Yeah, very good. Very good. And again, that's with this model. To be honest, think about this. If you used a 6 billion pound mass, that would start to change things. Because imagine, right? Or even if I just did the same problem like this, imagine this was not a book, but a long wooden board, right? Well, if I put something really heavy on here, isn't the board itself going to warp? Right? And that's going to cause some significant problems with our model. And so what if it actually starts digging into the surface? Then it's not so simple. Yeah. Or imagine like you're walking in golf shoes or high-heeled shoes on foam. Well, clearly the shape of the object starts to matter when you start to literally pierce into the shape, and then that's a different type of problem. But assuming we're talking about a problem where something's still just resting on top of a surface and not starting to dig into it, this model can somewhat apply with any mass. Is that good, Jake?
Yeah, thanks.
Yeah, obviously there's definitely going to be a limit at some point. Okay, let's take a look next here. All right, I'm going to let you guys try this one on your own later. And I want to kind of work on this one here. Okay, and so we'll start off here. I'll let you look at it for a second. Mass M1 is on an incline. It's connected to mass 2 over a pulley. Excuse me. System is released from rest when M2 is height h above the ground. Coefficients of friction are mu static and mu kinetic. Assume M2 is going to move towards the earth. All right. First question here. What conditions apply if the tension on each side of the pulley is equal? Remind me.
Constant acceleration. Is that?
Nope. Wait. I want the tension on each side of the pulley to be equal. That doesn't necessarily mean the acceleration is going to be equal, because the tension could be a really small number or a really big number.
It's something to do with acceleration, right? They're constant, not necessarily.
I'm thinking about this object right here.
Is it massless?
We need a low mass or massless pulley. What else?
Frictionless. axles.
Yeah, massless. And that's what I meant to be going for. Sorry if my question was misleading, Jake. I was going for that stuff.
Oh, okay.
You know what I'm saying? Poorly worded. That's all right. It gets the point across. Just trying to remind you that, oh, yeah, this isn't always true, but we're going to assume this is true. If we have a massless pulley with a frictionless axle, then we can assume the tension is the same on each side. Which condition allows us to say the acceleration magnitude are equal? The accelerations of the two blocks. What allows us to say that?
A massless string.
Nope.
The inextensible string.
Yeah, non-stretchy string. So inextensible string. Gee, what do you think part C is? Oops, I forgot an N. What do you think part C is? If you want the acceleration to be constant,
The massless
that's
string.
yeah, because right, if the string has mass and you transfer some mass from here to there, that's when acceleration would change. So if it's not stretchy, that means 1 and 2 are going to move the same amount, which means they'll have the same, each block has the same acceleration magnitude. And then that magnitude will be constant if you have a massless string. Now, obviously, massless is kind of a BS term. What we really mean is negligible mass compared to everything else. So I'm just going to put STR for string. All right, so that's just a reminder when these things apply. We're always going to assume those for this course, but later on we won't in a future course. So let's just assume we've answered those three. All right, how about this one? How should tension in the string compare to M2G? What are your thoughts?
M2G needs to be bigger than tension because it's falling downwards.
Exactly. Now, does this problem, do you think this thing is accelerating or not?
I would say so.
What gives you that clue?
Moves towards the Earth.
Okay, so we know it's going to move towards the Earth, but how do we know it's not just moving at constant speed?
It starts from 0.
Yeah. So something starts from rest and then starts moving. Clearly, it's not just moving at constant speed, it's accelerating. So that's a sign that this thing is accelerating. And that means that T should not equal mg for this block, right? We know that the downwards force should be larger than the upwards force. Otherwise, it wouldn't accelerate downwards. Okay, so take a second and do part E, this one here. Draw the FBDs, do the force equations, and then we'll meet up, okay? So you take a second to do that. And I'm going to get it on my board too. .16. I'm going to write down what's given in the problem. So when I read this problem, it looks like they gave us mass 1, mass 2, h, which is some distance above the ground, the coefficients, and then notice in the figure, it indicates the angle. So I'm going to assume for right now that we know that angle because it is given in the figure. So I'm going to assume we know the masses, G, which is, unless otherwise specified, I'm assuming we're on the planet Earth. So theta, H, and the mu's there. That's a mu. All right. We need to draw some FBDs. I'll catch up here. All right. So anybody that wants, unmute and give me a force on either picture. Just tell me what to do.
So we've got gravity on FBD1 and
FBD1. Okay. So which way does that point?
Straight down.
Okay. So what should I write next to this arrow?
M1G.
Nice. You remember the subscript. Okay. Somebody else?
Friction on the FBD1.
Friction. Which way does that point?
To the bottom.
Let me give you some tips on word. You can either say up the plane or down the plane.
Down the plane. Down the plane.
Which way does it point? Sorry.
Down the plane.
Down the plane. It moves up the plane, so opposite that is down the plane. Nice. Okay. What else we have?
Tension.
Which way does that point?
Up the plane.
On block 1, it points up the plane. What else?
And normal force.
Okay, and which way is that?
Up and to the left.
Yeah, so then perpendicular to the plane, which in this case is up and to the left. Hopefully I'm drawing it straight. That's pretty close. Now, sometimes I'll do this right here just to help myself out. This is not an FBD because all of the bodies are together. But if this is theta, this is 90 minus. I could see which way to draw it here. So I could see that that's theta, right? I eta theta is my new fraternity. All right. How about this block? Are we all done with that?
We need a tension force going upwards.
Okay. And then which way, let's start with block 2. Which way was 2 accelerating?
Down.
Okay. So I'm going to put that in here. So which way is block 1 accelerating?
Up the plane.
Mm-hmm. What's a logical coordinate system? Let's start over here. This one's nastier. What's the logical coordinate system? Rotated or not rotated? Do we want to use a standard XY or do we want to rotate it?
Rotated.
Yeah, what's the advantage of that?
You only have to break up gravity.
Yeah, which, oops, I already did it too. My bad. So I guess I was giving you a hint. Sorry about that. It's just, why wouldn't you choose this coordinate system? You only have to split up one thing, so it's much easier. So now if we go this way, again, just letting my hand, I'm going to do this for this coordinate system. So this one's going this way. Seems logical to go like this. Even though at first that probably seems super weird to you. Hopefully that's starting to feel somewhat natural now. What do you think? Did we forget anything? I think I forgot to label something. Was this tension, I think? What's this side right here? mg sine or mg cos?
M1G cosine.
Oh, nice. Thank you for reminding me. I probably would have forgotten, but caught it later. But yeah, good. And this would probably be M1G sine then. Not always true, but usually it's cosine perpendicular to the plane and sine. Obviously, you know from that crazy quiz, it's not always true. All right, so in this case, I've forgotten what we're doing, but we might as well write the force equations now, right? So help me out.
So for the first FBD, you got
X
T
or
minus
Y?
X.
Okay.
So sum of all X equals T minus F minus mg sine theta. M1 G sine theta.
Correct. Is that the force equation?
Equals M1A.
Yeah, there we go. Nice. So AX in this case happens to be A. So we could write AX here, but again, all of it's in the X, so AX equals A. All right, somebody else? Let's do the Y equation for that same block. What do you think?
We got N minus minus M1G cosine theta.
I agree. And I think that's going to equal.
Equals,
Oh, yeah. What's it equal?
well, it's not moving in the Y, so it equals 0.
Yep. And I guess the better way to say that would be not accelerating in the Y. Because even if it is
Right,
moving,
right.
that blah, blah, blah. Yeah, you know, whatever. So he's saying this is 0 because it's not accelerating up and down off the plane. It's going parallel to the plane. And so this was one of the other reasons we do this, right? Out of all these vectors, there was only one we had to do any trig. So do you agree I could cheat and just say that equals that?
Yeah.
Yep. So n minus this equals 0 is the same as n equals this. So the ups equal the downs. Nice job. All right, let's go over here to the x. What do we get in that direction?
M2G minus T equals M2A.
Beautiful. Color code that a little bit. All right. What would you do now? What's a good thing to do at this stage? We did it FBD. We wrote some force equation. What's a logical thing to do?
Read the problem.
Yep. Nice. And this doesn't always work, but it usually does. So, okay, we did that. This, huh? Any thoughts?
Or what is it called? The kinematics?
Nice. So, okay, what about kinematics?
Well, we know it starts at 0, and we know accelerates, and then we know delta y is
Please,
h.
careful. We said, remember, we rotated our coordinate system now. So didn't
yeah.
we call this x?
Oh yeah, you're right.
Okay, so what's v initial x is 0, he said. What's v final x? Known or unknown?
Unknown.
Unknown. What's delta x?
H.
Isn't it negative?
No, because of the coordinate
Nice.
system.
Because it goes down h. We also call down positive. I was trying to mess with you, but I can't mess with you too bad. You know it too well. All right, so delta x is positive h because down is positive. What about time? Do I know the time?
No.
What about acceleration?
You can calculate acceleration.
From what?
From the FBD, from the force equation.
From the FBD. So now we see what we got to do. We use the FBD to get A, then do kinematics on it. Whatever. All right, so let's get to work. All right, so how could I get the acceleration? I know how to do kinematics. If I could just figure out A, what would you do to get A?
So we could use the x equation on FBD2. We can get M2 on the same side, factor it out, divide it, and then subtract G, I guess.
Okay. What else can you do when you have a system of equations with this rotated? How could you get rid of T?
Oh, you can make a system FBD.
Stack them and add them, which is equivalent to a system FBD, right? Take a look. If you take this equation and this equation and you stack them and add them, negative T, positive T, tension drops out. We're still left with friction, though.
Well, we can figure out friction with because we know it's accelerating, so it would use mu kinetic times normal force.
Well, what's the normal force? So the idea is you take this equation and shove it in right here for F. Then you take this equation and this equation, stack them and add them. That gets rid of tension, the internal force. Friction gets replaced with something. You got a bunch of crap. You could solve it. Let's go take a look at the solution and see if it makes sense. We did some FBDs. Great. We say friction is this.
You're not sharing screen.
Oh, shoot. Thank you. Sorry. Sorry about that. So just take a look. Since we know M1 slides relative to the plane, we're going to use this equation. Well, I know N is M1G cos. So that's where I get this term right here. The friction becomes this term. Okay, just make it clear. This thing, I know that that's equal to that. So that goes into there, and that goes into here. That's all the friction. After we do that, it's pretty easy. Stack them and add them. You don't have to do this. You could have done what Jake was saying, which is basically solve for T, isolate T, and plug in. That also works just well, just as fine. I like this style, though, because look, it's faster to get to the acceleration, right? Because A ends up left all alone on this side almost instantly. Say, oh, I just factor out the M1 plus M2. There's that. And then you could solve for A. Shouldn't the mass drop out? What do you think? Yes or no?
No.
No, they're two different ones. And this is why we have to be careful with that 1 and 2 crap, right? It's 1, but there's 2. So it's a mix. It's just, there's nothing. It's just a mess. And then here's that kinematics equation. Oh, whoa. All right, that's fine. It's looking pretty good, right? I think that's pretty good on that. I'll pause for a sec. Any questions on that? What's up there? All right, let's go back and take a look at this one. I want you to read this question now. What is the minimum M2 required to cause M1 to slide up the plane or upwards? What do you think? How would you approach that? Go for it, Jake.
I guess, I mean, almost kind of the same thing as F, except we're going to have to find where acceleration is greater than 0.
Okay, so that's a good thing. Yeah. So if it's, okay, when you see this word minimum to slide upwards, What does that make you think? Does that, I don't know if that makes you think anything.
Oh,
I'm thinking about
maximum
friction. Yeah.
Which is which equation?
Mu static times the normal force.
Nice. And if it's, so another way of saying that is it's on the verge of slipping. This is a fancy way of saying it's on the verge, right? Do you agree with that? I think you do because
Yeah.
you said it right there. Huh. So we set friction equal to this. What else do you do? What else is going to be different? What did you just say, Jake, about acceleration?
Find where it's starting to change, so greater than 0.
Yeah. So greater thans are hard to solve. So let's just say A is equal to 0, right? And so if you have the largest amount of friction possible and your acceleration is still 0, that's what puts you on the verge of slipping. Any more mass than that, you would be slipping. And then the first 6 parts would apply. Does that make sense?
Yeah. Yep.
So basically, this means redo the whole problem, but change A to 0 and change mu kinetic to mu static. What do you think?
Makes sense.
And then let's go see what we get. So basically, you'd redo this whole problem, except this goes to 0, and this changes to an S. Right? And so you're like, oh, well, that's not too bad. I get this. I don't know if you believe that, but if A drops out, notice each term is going to have a G in it, and the G drops out, so it doesn't matter what planet you're on. And so M2 is going to equal this other crap, which is right there. And notice it's a mu static now. Sorry, I'll be yawning a lot today. I don't know. Okay. I don't know. What do you think? Some questions on that, or is this making any sense?
Makes sense. It's pretty cool.
Yeah. Oh, go
the
ahead,
fact
Jake.
that it doesn't the fact that it doesn't matter what planet you're on just kind of blew my mind a little bit. But
Isn't that weird?
I mean,
like this would work on the moon. Yeah.
Yeah, it makes sense. It's cool in the fact that gravity like doesn't matter in that case.
Mhm.
Like it's, I don't know.
Yeah. And then obviously if the gravity is, if it is accelerating, let's take a look and see. So we see that the mass required to make it slip doesn't depend on the planet you're on. However, notice that the planet you're on does matter once it does start to slip, because the acceleration is proportional to the free fall acceleration on the planet you are on. So obviously this would be your acceleration if you're in free fall, and it's something less than that, right? So all right. You could check the units, do all this stuff, but whatever. Remind me, what are the units on mu?
Nothing. It's
No
just a
units. You could see it right here. Friction equals mu n. This is a force in newtons. This is a force in newtons. So newtons. This has no units. So just remember that mu is a coefficient of friction. It's not friction. It relates to it most of the time. All right. Let's see what else we got in here. I don't know why. I just feel like I could take a nap. I'm just tired. Oh, let's stay positive here. Stay focused. Let me look back here. All right. At this point, we're getting a little bit better. We need to do some more problems here. We'll probably pick up 6.19 next time. 6.19 and 6.21 we'll do next time probably. So I want to point this out. At this point, I think you guys should do some problems, and I'll just answer questions, and Memo can answer questions. 6.17, if you think you know what you're doing, you could try this one. Now, if you're worried it's going to give you trouble, notice I say try this problem first. I don't know why I wrote it this way. It's like I just forgot about this problem. I always do this one in class and just wrote it on the board, but it was never in the book. But so I finally put it in the book. So this is probably easier than 6.17. So sorry about that. So if you want, or sorry, whatever I said, yeah. So you could try doing some of that stuff. If you want to go back and just work on, we skipped a problem here. If you want to go back and work on that one, what was it? 6.15, you could do that. Or if you want to work on this page, just practicing kind of your basics right now, or even 6.3.5 or any of these problems. So I think you guys should just work on problems right now and ask me questions. Before we set you loose to do that, Memo, could I get you to just say some reflections here, maybe? Do you have any advice or thoughts for them as they start getting into this?
Yeah, just make sure to try your pictures. Yeah, they got it down pretty good. I was watching the whole thing and everything it's pretty fluid. Let's see. Yeah, everything went smoothly. Let's see.
Any yeah, let's just let them get practicing then. So
Yeah,
there's basically nothing you could say now except practice your brains out.